Good morning. Today we're going to talk about stability and causality if we have the transfer function of a system. Now, we've talked about stability and we've talked about causality before. First, we started with the basic definitions, the basic definition of a stable system, a causal system. Then, we looked at specifically linear time invariant systems, and we had, for those systems, we had the impulse response. And so we looked at determining stability and causality if we had the impulse response. If you remember the definitions and you remember how to determine it with h of n, with the impulse response, good. If not, pause the video, go back and review it. Now, let's start out first with stability. As you saw when you went back and reviewed, we know that a system is stable, a linear time invariant system is stable when the absolute value or the magnitude of its impulse response, when summed from minus infinity to infinity, is not going to be infinite. And so if we have this condition, then the system will be stable. We'd like to be able to determine stability straight from the transfer function, right? If we have h of n, or if we have the transfer function, we could always get h of n and then try to determine stability. But it'll be easier trying to determine stability straight from h of z. Now, we know that the h of z is the z transform of h of n, right? H of n is the impulse response, h of z is the transfer function. And this would be the definition of a z transform. Now, we want something that looks like this here. And so let's take the magnitude of h of z. If we do that, then we'll have this. Now we know that the magnitude of the summation is less than or equal to the sum of the magnitudes. So we get this inequality. Now, again, comparing this up here with this down here, we say, well, they look similar and they'd be the same if z was equal to 1. So let's make z equal to 1. That would give us that h of 1, or the magnitude of h of 1, is less than this summation here, which we know comes from the summation of stability. So, if our system is stable, it means this summation is not infinite, which means that the magnitude of h of 1 is not infinite either, which is nice. Okay, so now h of 1 is the transfer function at z equal to 1. And if that's not infinite, right, we said that for some values of z, h of z is going to be infinite, and for some values of z it won't be infinite. For the values of z where h of z is not infinite, those we call the values of z in the region of convergence. So, if z equals 1 is in the region of convergence, then it means that the system will be stable. So when we want to determine stability, looking at the transform, the z transform, right, the transfer function, what we do is we look at the region of convergence. If the region of convergence includes 1, we say the system is stable. If it doesn't include 1, well, then the system won't be stable. So it's rather easy to determine stability. It's by inspection we can determine stability if we have the transfer function, right, with its region of convergence. How about causality? Okay, let's start again with the transfer function. Let's say it has a whole bunch of zeros and it has a whole bunch of poles. It's, in this case, n poles. Let's do a partial fraction expansion of the n poles. And now each of these terms can be inverted. Now each of the terms can be inverted in one of two ways depending on the region of convergence, right? We know from before that, for example, this term, or writing it either in positive values of z or negative values of z, it has two possible inverses, right? If the region of convergence is greater than the magnitude of the pole, this would be the inverse. But if the region of convergence is less than the pole, then this is going to be the inverse. So, what do we need for causality? Now we know, as you saw when you went back and reviewed, for the system to be causal, we need h of n to be 0 for n less than 0. So for negative values of n, h of n must be 0. And then we come up here and we look at the two possible inverses. We say, well, for the system to be causal, we need this inverse, not this inverse, because, right, the second inverse that's here has values from minus infinity to minus 1. This one has values from 0 to infinity. And so this is the one we want. It means for the system to be causal, each term will have to be inverted this way. Now what does that mean? It means, of course, if we put all these things together, so each term must be inverted as this. So the region of convergence must be the magnitude of z greater than the magnitude of the pole. But this is for every term. In other words, we need z greater than pi for all I. Now, in general, the region of convergence is the intersection of the regions of convergence for each term. So we'd get this long thing here, right? Z greater than P1, Z greater than P2, etc. Now, since we needed greater than all of them, it would just be Z greater than the maximum of them. In other words, for the system to be causal, or if we want to determine a system is causal or not, we look at its region of convergence. If the region of convergence is greater than the largest pole, it's causal. If not, it isn't causal. Now let's go and look at this example. Let's say we're given this h of z with this region of convergence, and they ask us to determine its stability and its causality. We say, well, h of z has two poles, right? It has a pole at 0.3 and it has a pole at 0.2. Now the region of convergence is greater than 0.3, so the region of convergence is larger than the largest pole. So it means that the system is causal. We also look at the region of convergence, and the region of convergence is greater than 0.3. So z equal to 1 would be included in the region of convergence, and so we say that the system is stable. How about this one? Right, again, we have a system with two poles. This time, one pole is at 1.2, another pole is at 0.8, and we see that the region of convergence is between 0.8 and 1.2. Now, z equals to 1 is in the region of convergence, so the system will be stable. However, the region of convergence is not greater than the largest pole, so it's not causal, right? For it to be causal, the region of convergence would have to be greater than 1.2. And finally, what if they give us this system, and instead of giving us the region of convergence, they tell us it's causal? Now, this is very common. In a lot of problems, they give us h of z and they tell us the system is causal instead of giving the region of convergence. In other words, we can determine what the region of convergence is. Now, we look at this system. Again, it has two poles. It has a pole at 2 and a pole at z equal to 0.8. Now, it tells us it's causal, which means, of course, that the region of convergence is greater than the largest pole. The largest pole is z equal to 2, so the region of convergence is magnitude of z greater than 2. Now, if the magnitude of z is greater than 2, it means that z equals to 1 is not in the region of convergence. So this system will not be stable.